This resource is the third in a three-part series on polar coordinates. Part 1 defines polar coordinates. We consider how to convert from rectangular to polar coordinates and look at examples. We also discover how to convert from polar to rectangular coordinates and look at examples. Part 2 considers complex numbers. We consider the complex plane and how to graph complex numbers. We consider the polar form of complex numbers. We discover how to convert back and forth between the rectangular and polar form for complex numbers and look at multiple examples. Part 3 looks at de Moivre's theorem, which provides a method for raising a complex number to a power. The theorem is formally defined. We then solve examples, both for complex numbers given in rectangular or polar form. De Moivre's theorem provides a method for raising a complex number to a power. However, there is a condition for the theorem to work properly. The complex number must be written in polar form. This means that our complex number z must be written as r times the quantity cosine of theta plus I times the sine of theta. When we raise the complex number z to the nth power, we are really raising the entire quantity r times the quantity cosine of theta plus I times the sine of theta to the nth power. De Moivre's theorem says that if we have this situation, a simplified form of the answer equals r to the nth power times the quantity cosine of n times theta plus I times the sine of n times theta. Let's take a look at an example. Suppose our complex number z is 2 multiplied by the quantity cosine of 30 degrees plus I times the sine of 30 degrees. We want to find this number z raised to the 5th power. First, we write the entire polar form raised to the power. We apply de Moivre's theorem. This means that our complex number raised to the 5th power equals 32 multiplied by the quantity cosine of 150 degrees plus I times the sine of 150 degrees. What happens if our complex number is not written in polar form? Not to worry, we can use the following process to find our complex power. Convert the complex number to polar form. Use de Moivre's theorem to find the power in polar form. Usually, math teachers like the answer written in the same format as the original problem. So we will convert our answer back into rectangular coordinates. Let's see an example. Suppose we have the polar number z equals 3 minus 4i, and we want to find z raised to the 5th power. First, we need to convert to polar form. In other words, we need to solve for r and theta. We use the formula r equals the square root of the quantity a squared plus b squared. We plug in our values of 3 and -4 for a and b, respectively. Solving, we find that r is 5. Now we want to find theta. Because our real value is positive, theta equals the inverse tangent of the ratio of b to a. Plug in our values. This tells us that theta is -53.1 degrees. So our complex number in polar form is 5 times the quantity cosine of -53.1 degrees plus I times the sine of negative 53.1 degrees. Now we can use de Moivre's theorem to find our power. First, a quick reminder of de Moivre's theorem. The complex number z raised to the nth power equals r to the nth times the quantity cosine of n times theta plus I times the sine of n times theta. We plug in the polar form for the complex number we just found, using the formula to quote-unquote distribute the raised to the fifth power. So in polar form, our z to the fifth power equals 3,125 multiplied by the quantity, the cosine of negative 265.5 degrees, plus I times the sine of negative 265.5 degrees. To convert back, we distribute the r through the parentheses. So we plug in the polar form we just found. Doing the math, we have the complex number negative 245.2 plus 3,115.4 I.